Welcome back to Bite-Sized Breakthroughs, your podcast for the latest in tech and AI research. Today, we're diving deep into a fascinating paper exploring how large language models can be harnessed to control real-world computers. I'm Alex Askwell, and joining me is Dr. Paige Turner, a leading researcher in this field, and Professor Wid Spectrum, an expert on the broader implications of AI.
Thank you for having me, Alex. It's exciting to be here discussing this cutting-edge research.
It's great to be here. This is a topic that's gaining significant traction as AI increasingly interacts with the real world. So, Paige, let's start with the basics. What's the central problem this research addresses?
Sure. The paper focuses on the challenge of directly controlling a computer's screen interface using a vision language model, or VLM for short. VLMs are good at understanding and generating text, but they haven't been very adept at interacting with a computer screen in a continuous and meaningful way. Think about how we use our computers. We click, type, and navigate using a graphical user interface, or GUI, which is a visual representation of the operating system. This paper proposes a system called ScreenAgent that enables VLMs to bridge this gap and control a real computer screen.
So, how does ScreenAgent work? It's fascinating that we're talking about a language model controlling a physical system.
Right, it's a bit mind-bending. The paper introduces a three-phase control pipeline for the VLM agent. The first phase is planning, where the agent receives a task prompt like open a document and find the information about databases, and breaks it down into smaller steps. It then generates a plan in JSON format, a way of organizing data that computers understand. Each step specifies an action like open browser or search for databases in the browser.
That's interesting. So, the model actually thinks through the process. What happens next?
The next phase is acting. The model takes the generated plan and translates each step into low-level mouse and keyboard commands, again in JSON format. These commands are sent to a real computer screen through the VNC protocol, which allows remote control. The environment then captures the screen state after each action, so the model can see the results of its actions.
So, the model is actually seeing what's happening on the screen, like a real user, and adapting its actions based on that feedback.
Exactly. The final phase is reflection. The model analyzes the screen after each action to see if it achieved its goal. It might decide to retry the same action if it didn't work, go on to the next subtask if it did, or even reformulate the entire plan if it realizes its initial strategy isn't working. This allows for a more dynamic and adaptive control process.
That's really impressive, Paige. So, the model is not just blindly executing instructions, but actively learning from its environment and adjusting its approach. I'm sure this is quite different from how previous models have tackled this problem. What are some key differences from existing methods, Professor Spectrum?
You're right, Alex. This work pushes the boundaries of what we've seen in computer control agents. Previous models, like CogAgent, were good at understanding the GUI and planning actions, but they lacked the ability to execute those actions in a continuous and adaptable way. They were essentially stuck in a thinking chain without the ability to interact with the world and learn from their mistakes.
So, ScreenAgent is different because it incorporates a reflection phase to allow the model to learn and adjust in real time. But that's not the only innovation, right?
Exactly. This research also introduces a new dataset called the ScreenAgent Dataset, which is specifically designed for training and evaluating computer control agents. It includes screenshots and action sequences corresponding to a variety of everyday computer tasks, like browsing the web, managing files, or playing games. It's a massive resource for researchers in this field, as it's much more comprehensive than existing datasets that primarily focused on web browsing or Android UIs.
It sounds like a game changer for the field, Professor Spectrum. How do you see this impacting the development of AI in the long term?
Well, Alex, this research has far-reaching implications. It demonstrates the potential for VLMs to interact with the real world in a way that goes beyond just generating text. Imagine a future where VLMs can act as your personal assistants, seamlessly navigating your computer and performing tasks on your behalf. This research is a critical step towards building more general and autonomous AI agents that can assist humans with a wide range of tasks.
That's an exciting vision. Let's talk about the specific results of the study page. What were the key findings?
The researchers evaluated ScreenAgent's performance against GPT-4v, a powerful multimodal language model from OpenAI, as well as other state-of-the-art VLMs. The results showed that ScreenAgent achieved comparable results to GPT-4v in terms of overall task completion, but it outperformed the other models in terms of precise UI positioning. This means that ScreenAgent is better at accurately identifying and clicking on specific elements on the screen. For example, the paper shows that ScreenAgent successfully clicks on the correct button or menu item with high accuracy, while other models often miss the target or click on unintended elements.
That's impressive, considering that precise positioning is crucial for interacting with a computer screen. However, there are limitations, right?
Yes, absolutely. The researchers acknowledge that ScreenAgent still has limitations, particularly in the planning and reflection phases. GPT-4v outperformed ScreenAgent in these areas, demonstrating the importance of common sense knowledge and task planning abilities. So, while ScreenAgent is good at carrying out actions, it needs further development to better understand and adapt to complex tasks, especially when dealing with unforeseen situations.
That's an important point. This research, while impressive, is still very much in its early stages. What are some of the key areas for future research, Paige?
Well, Alex, there are several exciting directions to explore. The researchers suggest developing more robust and precise visual localization capabilities for VLMs so they can more accurately interact with UI elements. They also want to improve the model's reasoning and adaptive abilities by developing more sophisticated planning and reflection mechanisms. Finally, they want to expand the model's capabilities to handle videos and multi-frame images, allowing for even more dynamic interactions with the computer screen.
Those are all very promising areas for future research. Professor Spectrum, do you have any thoughts on the broader impact and potential applications of this research?
Certainly, Alex. This research has the potential to revolutionize how we interact with computers, making them more accessible and automating tasks that are currently performed manually. Imagine being able to tell your computer to schedule a meeting with Dr. Turner next Tuesday at 10 a.m. or create a presentation on the latest AI breakthroughs. This technology could significantly enhance productivity and create new opportunities for individuals with disabilities who may struggle with traditional computer interfaces.
That's a powerful vision, Prof. Spectrum. But as with any new technology, there are ethical considerations. What are some of the potential challenges we need to be aware of?
You're right to raise that point, Alex. The potential for misuse of this technology is a significant concern. For example, it could be used to automate malicious tasks like spreading misinformation or bypassing security measures. We need to carefully consider the ethical implications of this research and develop robust safety mechanisms to ensure that this technology is used responsibly.
It's a critical conversation to have, Prof. Spectrum. Paige, any final thoughts on the significance of this research?
This research represents a major leap forward in the field of AI agents. It demonstrates the potential for VLMs to not just understand the world, but to interact with it in a meaningful way, controlling physical systems and automating tasks. While there are still challenges to overcome, this research is a testament to the rapid progress being made in AI, and it has the potential to reshape how we live, work, and interact with the world around us.
Thank you both for joining us on this fascinating journey into the world of AI-driven computer control. This is a topic we'll undoubtedly be discussing more in the future. Stay tuned for more bite-sized breakthroughs.